Okay. This abstract here, I've submitted to EasyChair, but it was not published on the conference page due to some technical reasons. So now I repeat it here. Lambek's paper, The Mathematics of Sentence Structure from 1958, introduced syntactic calculus as an extension of the type reduction procedure for categorical grammars due to Ajdukiewicz and Bar-Hillel. This calculus was later called Lambek calculus and extensively studied in computational linguistics as a basic type logic for these grammars. In 1961, Lambek proposed a non-associative version of this calculus. Here we denote this calculi by L and NL, respectively. Lambek presented both calculi in the form of Gentzen-style sequence systems and proved the cut elimination theorems for them. A characteristic feature of this system is the lack of structural rules, exchange, weakening, contraction, which are admitted in sequence systems for classical logic and intuitionistic logic. The connectives are multiplication and two implications, backslash and slash. The latter are also called divisions or residuation. In the, here is something bad here. In the logical community, this should be, maybe I cannot, it would be better for me. One also considers many extensions of L and NL. In the logical community, in particular in substructural logics, L enriched with the constant 1, the unit for multiplication, and lattice connectives and constants is called full Lambek calculus, the FL, and regarded as a basic substructural logic. Substructural logics are defined as extensions of FL by new axioms and rules. The name substructural logic is justified by the lack of some structural rules in their sequence system. Propositional linear logic, PLL, of Girard, 1987, enriches the commutative FL with negation, satisfying the double negation law and two unary modalities called exponentials. Its fragment without exponential is called multiplicative additive linear logic, MALL. Lambek connectives, the unit, and negations are referred to as multiplicative, and lattice connectives as constants as additive. Further extensions admit various modalities, Kleene iteration, the distributive laws for lattice connectives, and others. In this talk, I focus on sequence systems for different logics from this family. More precisely, I consider two properties of them, cut elimination and interpolation. I'm concerned with some consequences of these properties which are interesting for computational linguistics. The cut elimination theorems were proved for almost all systems considered here. This talk, however, discusses generalized versions of these theorems, working for logic extended with non-logical axioms, here called assumptions. As a consequence, these logics are strongly conservative extensions of their language-restricted fragment. This means that they preserve not only the probability in pure logic, but also the probability from assumption, the consequence relations, as called. Like in foundations of mathematics, first-order theories are even more important than the pure first-order logic. I believe that Lambek logics with assumptions can find useful applications in linguistics. I will say a bit more later on. Furthermore, hello? Please? Furthermore, applying cut-free systems for pure logics, one constructs syntactic interpretation of stronger logics in weaker logics, admitting Lambek's restriction. The antecedent of any sequent must be non-empty. It was considered in my paper. Now, Craig interpolation lemma, known from logic, states that for any probable implication phi implies psi, there exists an interpolant chi such that chi uses only non-logical symbols common for phi and psi, and both phi implies chi and chi implies psi are probable. Now, in such propositional logics, in fact, which are considered here, these non-logical symbols are simply atoms or propositional variables. For L, the Lambek calculus, the interpolation lemma of Roda from 1991, formulated for a sequence system for L, states that for any probable sequent, gamma 1 delta gamma 2 arrow A, there exists an interpolant D such that both gamma 1 D gamma 2 arrow A and delta arrow D are probable, and the number of occurrences of any atom in D is not greater than these numbers for delta and for the context. Roda's lemma is essential in the proof that Lambek grammars are weakly equivalent to context-free grammar. But for multiplicative, non-associative logics, if gamma with a sub, we call bunch, a sub-bunch delta, arrow A is probable, that the interpolant D of delta can be found among sub-formulas of the formulas in the sequence. So this is in essential, this works only for non-associative logic, non-associative logic. For associative logic, it is usually not a subform. For systems with assumptions, one must add subformulas of the formulas in assumption. For NL with assumptions, the latter lemma was proved by myself and later extended to other logics by several authors. Some interesting consequences are the p-time complexity of the consequence relation. It means probability from assumptions for these logics, and the weak equivalence of categorical grammars based on this logic, also with assumptions, with context-free grammar. Now, I briefly recall Lambek calculus, the basic Lambek calculus. The calculus NL in algebraic form, so ABC denote formulas, it's also called types, formed out of atoms, PQR, and connectives. Here, because I could say variables here, but in fact, in categorical grammar, so these atoms are treated as constants, denoting some particular category. And connectives, multiplication, and these two divisions or implications. The axioms are identity, A arrow A, and the inference rules are these are some, the double line means that the rule acts in both directions, top down and bottom up. And the rule K. The algebraic form of L, the Lambek calculus associative, is obtained by affixing two new axioms which express the associative law here. So in models, in algebras, the models of the non-associative logic are residuated groupoids. Those are partial ordered structures which can be axiomatized exactly that the axioms of partial order, and here the arrow is interpreted as the partial order, and two binary operations where here we replace the rule by implication. If A is not greater than less or equal to B and B less or equal to C, then A is less or equal to C, and here equivalences, yes, implications in both directions. So these are models. I will not speak much about models here on this talk. Now the following rules are derivable in both an L and L. These are monotonicity rules, yes? And especially the first one, they are essential later, because in fact, in sequence systems, one uses this monotonicity. Now, here some laws probably in the non-associative Lambek calculus. These are so-called application laws, type raising, expansion, composition, and switch. These two on L4 and L5 can be proved in L only. They need associativity. Some names here refer to semantics, because in type theoretic semantics for categorical grammars, then expressions of type, of these functor types here, I interpret it as maps from the domain of type A to the domain of type B. Yes? So this means here, and this corresponds to application. No, so here there is a law of compositions of two maps. Let us briefly discuss the linguistic meaning of this formalism. The basic interpretation refers to syntax. Sigma is the lexicon of some language. Sentences and other phrases are represented as strings of words from sigma. Types represent certain sets of strings corresponding to syntactic categories. The order is inclusion. Atomic types represent some basic categories. For instance, S the category of declarative sentences, statements, N the category of paper nouns, the uppercase N the category of common nouns. Compound types represent functor categories. A string X is of type A under B. If and only if, for any Y of type A, the concatenation YX is of type B, and similarly for the other type, B over A. One says that X is a left-looking functor from category A to category B. Also, Z is of type A times B, if and only if Z equals XY for some X of type A and Y of type B. In non-associated framework, strings are replaced by bracketed strings or phrase structures. One writes X, Y in parentheses for XY. So, N under S represents the category of verb phrases, for instance, works. N over S, N under S, and this over N, the category of transitive verb phrases, for instance, likes. This, the category of full noun phrases, for instance, every boy. This, the category of determiners, every, for instance, and so on. This law is an instance of L2, type raising, says that every paper noun is a full noun phrase. Here we ignore agreement, flexion, etc. To regard them, a finer typing is necessary. For instance, S1 for statements in present tense, S2 for statements in past tense, NI for I from 1 to 3 for subjects in the I's person. Then likes is of types N3 over S1, like of types N1 over S1, and N2 over S1, under S1. And liked is of can be assigned all these types, Ni over S2. One may use N as a general type of subjects, assuming that Ni arrow N for all I, and similarly S as a general type of statements, assuming Si arrow S. This naturally leads to Lambek calculus assumption. Then liked can be assigned type N over S2, and this is provable. This sequence is provable by the second rule of monotonicity. Here are very simple examples. we can give many other arguments for introducing assumptions to this calculus, maybe a bit later. Categorical grammars. A categorical grammar provides the owl information on the particular language by types assigned to words. This is the principle of lexicalism. Other types are derived by the logic underlying the grammar, common for all languages. One may assign many types to one word. We assign, for instance, to John two smiles n over under s. This yields John smiles s. Since this sequence is probable in both NL and L, we assign to often this type. This is the types of adverbs. This yields John often smiles s, since this is probable in L. In NL, this is probable. We must add brackets here. So we obtain the following phrase structure. John often smiles is assigned S. We assign boy the type of common noun, some the type of determinants. This yields some boy smiles as in grams based on L, and some boy smiles in grammar based on NL. So one comment here. Of course, the non-associative Lambek calculus is much weaker than the associative Lambek calculus, but it can be naturally used to describe languages consisting of phrase structure, not strings without any structure on it. And some linguists, for instance, Modgat or Mori, used this calculus, but usually extended with some other tools which increase its expressive power. Now, for instance, unary modalities. So in Modgat's paper, one can find many, and Moritz also. Unary modalities and some types preceded by such a modal operator. One adds new axioms that to obtain some, to explain some linguistic construction. For instance, the type diamond A can commute with an arbitrary type B. For me, it seems that because they usually use this new axioms, new logic with some new axioms for modalities, to explain some particular linguistic phenomenon, some particular construction. So they use them to some special types. So instead of introducing an axiom which can be applied to all possible types, yes, it would be more reasonable perhaps to introduce an assumption that for these particular types, we have here this commutation, that these types commute. No, but this is my reason. This is another argument for considering assumptions. So the principle, the radical principle of lexicalism can be weakened in some situations. Now, sequence system for L and LL. For L, a sequence is of the form gamma arrow A, where gamma is a non-empty sequence of type. The non-empty, it is essential for this is Lambek restriction. Commas in gamma are interpreted as multiplication. The axioms are identity. The rules are as follows. Here's the left introduction of multiplication, right introduction of multiplication, left introduction of this implication, and right introduction of this implication. Similarly for the other implication. And the cut rule, and now here, for instance, to justify it in models this rule? No, we must need that because these two reduce arrow B is false, but here they are in constant. This is replaced. So we use here the monotonicity, in fact, of multiplication. In these rules, the right introduction rules, the sequence gamma must be non-empty. This is a Lambek restriction. Removing this constraint yields a stronger systems L epsilon, admitting empty antecedents of sequence. In non-associative Lambek calculus, the antecedent of a sequence is a bunch. It is a term introduced by David Pym, I think. A bunch is a single formula or gamma, comma, delta, where gamma and delta are simple bunches. A context is a bunch gamma with one occurrence of a special atom, and gamma delta denotes the substitution of delta for the special atom in this context. The axioms of an L are identity. The inference rules are as follows. This is similar, but everything must be here bracketed. We must use structures here. An L epsilon admits the empty bands, here denoted by epsilon, as the antecedent of a sequence. One assumes that these holds in meta theory, and one writes simply arrow A instead of epsilon A. Then A is a probable formula in the sequence. In NL and L, there are no probable formulas. We can only consider sequence. Now cut elimination. The cut elimination theorem. Every sequence probable in the logic has a proof with no applications of cut. This theorem was proved for the sequence systems for L and NL by Lambek, two papers, by proof-theoretic method. The same proofs work for L epsilon and L epsilon. Main consequences. First, every probable sequence has a proof such that every formula appearing in the proof is a subformula of some formula occurring in the sequence. This is the subformula pattern. The logic is a conservative extension. It follows from one. The logic is a conservative extension of its all language restricted fragment. For instance, L is a conservative extension of L restricted only to implications without product. Third, if the size of the conclusion of every rule is not less than the size of each premise of this rule, then the logic is decided. This holds for the four logics considered above. We also consider the consequence relation, that this sequence is probably from S, where S is a set of sequence called assumptions. In opposition to axioms, the set of assumptions need not be closed under substitution. The extended subformula pattern. If a sequence is proven in the logic from a set of assumption S, then it has a proof from S such that every formula appearing in the proof is a subformula of some formula occurring in the sequence or in assumption. For NL and L, this was proved by myself in this paper, and there will be on reference, by a model theoretical argument. If a sequence has no proof satisfying this property, then there exists a model such that all assumptions are true, but the sequence is not true. And by the completeness of these logics with respect to some classes of models, this means, this yields that it is not probable, that the sequence is not probable. My PhD student, Zelin from China, found a proof-theoretic argument. For NL and L, one can only consider assumptions. Consider assumptions, here is a mistake, is redundant, of the form A arrow B, of course, because some commas in the antecedents are interpreted as multiplication, we can replace them by multiplication, obtain a single time. For NL, each assumption A or B is replaced by the following rule, as cut here. Of course, it is different for different assumptions. Gamma with B arrows C and delta arrows A, two premises, gamma delta arrows C. So this can be obtained by two applications of cut. But here, this A, B are fixed, are just these formulas from this assumption. Yes? For L, this will have the following form. In this logics with empty antecedents, one can only consider assumptions of the form of Z, because every sequent is deductively equivalent to a sequent of this kind, each of this form. Each assumption arrow A is replaced by the following S-cut rule. Here simply this A disappears, so one must reduce this gamma epsilon to a bunch without explicit occurrences of the empty structure. And for L with epsilon, it looks like that. One proves the cut elimination theorem in the form. Every sequent probable from S has a proof not applying cut, but it can use some rules as cut. So only cut in this form, restricted to this rule connected with assumptions. This yields the extended subformula property. Accordingly, each logic preserves the consequence relation of its language-restricted fragments. So not only the conservative extension, but we say that it is a strongly conservative extension that preserves the consequence relation in the smaller language. This does not yield decidability. It is known that the consequence relations for L and L epsilon with finite S are undecided. Now one consider this different extension. The same can be shown for different extensions of Lambek calculus. Full Lambek calculus, FL, enriches L with additive connectives, and or with the corresponding rules. In fact, interpreted in lattice by meet and join. Here for end, left, right, for or, left, right. For F and L, the left introduction rule are as follows. The right are the same, and left are, but here, of course, if we omit external outer parentheses here, that will be the same rules as in this way. In the same way, one obtains FL epsilon and FNL epsilon from L epsilon and L epsilon, respectively. Here, my notation differs from that in substructural logic. In the literature on substructural logics, full Lambek calculus is defined as and denoted by FL, but in fact, in my notation, it is FL epsilon with constant 1, admitting the following axiom and the following rule. Here is a unit for multiplication. Optional, one adds a constant 0 with no new axioms or rules. One defines substructural negation. This A tilde, A under 0 and A minus 0 over A. One can also add some structural rules, exchange, weakening, contraction. They only modify the structure of the sequence, but don't introduce any new connective. We omit non-associated version of these rules, which are similar. In logics with exchange, the formulas A under B and B over A are equivalent. That means arrows in both sides are probable. Both are replaced by A implies B. In logic with weakening and unit, one proves that A arrow 1 for NA. Hence, 1 is interpreted as the greatest element in models. Each logic is a strongly conservative extension of its language-restricted fragment. A syntactic interpretation. Here, the cut elimination allows to interpret systems admitting empty antecedents are preferred by logicians. They yield probable form. Systems not admitting empty antecedents are preferred by some linguists, for instance, Modgard, Morris, and others. For instance, in L epsilon, the types n and n over n, and this type are equivalent. Now here is one more, one redundant parenthesis. Why linguists want to distinguish them? N over n is assigned to adjectives and the other type to adverbs. In my papers, here was in conference paper and the other on a journal, the former systems admitting empty antecedents are interpreted in the latter, not admitting empty antecedents. One defines two interpretation maps, P and N. P is applied to positive occurrences and N to negative occurrences of subformulas in the sequence. This is more elegant for logics with this additive connectives, because without additive connectives, in fact, these maps are many-valued. So assign several formulas to one formula. So both P on P and NP is equals P for atoms P. Here is simple for conjunction, and similarly for disjunction. N for multiplication is the same simple formula, but here is different. P on Z is equals Z if neither arrow A nor arrow B is proven. It is this if arrow A but not arrow B is probable. And here all possibilities are here considered. And now here PA under B is NA under P or B, PB over NA, and so on. Again, here we refer to probability or unprobability. One proves, which is omitted here on the slides, that always one can prove in the stronger logic with empty antecedents that always NA arrow A is probable and A arrow PA is probable. Now the main theorem is the following. For every sequence gamma arrow A, where gamma is non-empty, this sequence is probable in the stronger logic FL epsilon, if and only if the sequence N gamma arrow PA is probable in FL. Of course, N gamma means that we apply this N to all formulas in the sequence gamma. This also holds for logic with structural rules and non-associative logic. One essentially uses cut elimination for the pure logic, so it cannot be generalized for logics with assumption. Yes? But our scope of this logic is here, pure logic is obtained. Now, some interesting consequences from that, for instance, the undecidability of the stronger logic yields undecidability of this weaker logic. Yes, and so, for instance, so one can obtain such consequences. Now, another central topic of this talk is interpolation. Interpolation, in our sense, reverses cut elimination. Every probable sequence, also from assumptions, can be presented as the conclusion of cut, where the cut formula is a sub-formula of some formula appearing in the sequence. or in some assumption. So more precisely, the interpolation theorem. Let gamma delta, but this is also for only for non-associative systems, this form of interpolation. Let gamma delta rho A be provable from S. There exists a formula D being a subformula of some formula in this sequence or in sequence from S, such that both gamma D rho A and delta rho D are provable from S. D is called an interpolant of delta in gamma delta rho A. This theorem was first proved for NL by myself. The proof works for NL epsilon, also with unit. One proceeds by induction of proof satisfying the extended subformula pattern. Yes, but we can use the cut rule. We can use the cut rule, but we must all formulas must be taken from some finite set of formulas. And now some notions here needed here. Let T be a set of formulas closed under subformula. A T sequent, this is a definition, consists of formulas from T on. A sequent of the form A arrow B or AB arrow C is said to be basic. We fix a finite set of assumption S. Every assumption is of the form A arrow B with AB in T. We construct a set C on T, which consists of all basic test sequence probable from S in an L. The construction, so there's finitely many such sequence, but the construction can be performed in polynomial time. We omit details. This is quite sophisticated here, this proof and the construction. Therefore, the consequence relation for an L is P time. Furthermore, every probable T sequent, now already not necessarily basic, this gamma may be longer, can be proved from C on T using cut only. Such derivations use of cut with finite, where we use only finitely many formula, a fixed finite set of formulas here. This is essentially a derivation in a context-free grammar. Therefore, the categorical grammars based on an L with finitely many assumptions generate context-free language. Bulinska, my former PhD student, proved the same results from NL epsilon with unit, and Zelin for some modal extensions of an L. Here with unit and this empty antecedent, there's some problems that not only that simply not similar as in context-free grammar when we eliminate null rules, yes, because they may using these rules, so the conclusion is shorter than the premise. For logic with additive connectives, the interpolant can be a lattice combination of formulas from a finite set. In general, this yields an infinite set of possible interpolants. It is known that the consequence relations for FNL and FNL epsilon are undecided. It is the Czech Logicz and Kwalowski proved. They are decided for FNL and FLL epsilon enriched with the distributive law. It suffices to add to the system one new axiom, so the other laws are provable already. The interpolation theorem can be proved with a finite set of possible interpolants. Using the distributive laws, every such combination of formulas from T can be transformed into its conjunctive normal form. Omitting repetitions in this form, one obtains a finite set of this form. This yields the decidability of the context freeness of languages generated by categorical grammars based on this logic. This is not my paper, but not the p-time complexity. Not the p-time complexity. The consequence relation for this logic with additive constants is x-time complete. It is shown by Scato and Van Alten. One also considers the extension of an L with two negations, satisfying this and this. What? Maybe I skipped. Oh, non-associative linear logic. I skipped this slide. Can you see it? Can you hear me?
Yes.
Yeah. So this is the last part of this talk here. In the last year, some related results were obtained for the multiplicative fragments of non-associative linear logic. Now, this is not a very popular topic in the community of linear logicians, but recently non-associative linear logic have been studied by authors from the community of computational logic. For instance, Blaisdell, it will be in references, Kanovich, Szczedrov, Kuznetsov were co-authors. The first logic of this kind was introduced by de Groote and Lamarche in 2002 under the name classical non-associative Lambek calculus. The logic can be presented as the extension of an L by negation, satisfying the double negation and the contraposition laws. Now here this double arrow means that we have arrows in both directions. This system does not admit cut elimination in this presentation, but in the cited paper, this here. A cut-free one-sided sequence system is given, and its p-time complexity is proved. The system is shown to be a conservative extension of an L. I further studied this system in a later paper. I used a dual one-directed sequence system and proved cut elimination theorem and the interpolation theorem. In fact, some version of the interpolation theorem. As a consequence, the logic is shown to be a strongly conservative extension of an L, not only conservative, preserves the consequence relation. Categorical grammars based on this logic, also with assumptions, generate context-free language. One also considers the extension of an L with two negations, satisfying double negation laws and the contraposition law in this form. Like in non-commutative, multiplicative, additive linear logic of Abruzzi. And in 2017, a paper in the Bulletin of the Section of Logic, I presented a one-sided sequence system for this logic called involutive non-associative Lambek calculus. It proved the cut elimination theorem and the p-time complexity of the pure logic. The proof uses an interpolation theorem. The methods are proof theoretic in this paper complete. The complexity, even the decidability of the consequence relation remains an open problem for this logic. In a later paper, I studied an extension of this logic by a unary modality, this is a strongly conservative extension, and obtained similar results by model theoretic tools. Categorical grammars based on this logic are shown to generate context-free language. And my last PhD student, at this moment, some results have been adapted for logic with additive connectives and the unit by Wojciech in his PhD thesis and some publications. Now some selected references, not all, so I omitted here because there are only 2 pages. This Abruzzi, these are classical papers, yes, of Abruzzi, Jeter, and of cyclic linear logic, and some other. So here is this 5 authors which consider, they published several papers on this topic. My paper, this is 2005, Lambek calculus with non-logical axes. Now, here I considered the full non-associative Lambek calculus with distributive laws. In fact, more general, because non-associative Lambek calculus may be naturally generalized by introducing unary connectives, modalities, ternary connectives, and so on. Yes, and these results can be shown for all these systems. Another point of view which justifies an interest in non-associative logic is that we can look at these Lambek connectives as binary modal operators. And multiplication corresponds to the binary diamond, and the implications, in a sense, to a binary box corresponding to the diamond. From this perspective, the NL is a purely modal part of some modal logics with binary modalities. One can add to this system connectives of classical logic, and thus these operators will be modal operators, we have classical or intuitionistic. This was considered, for instance, in papers by Frances and Kamiński, and also in my papers from 2001. I don't hear so another justification for non-associativity, because associativity and unit are not natural from this perspective. And here are this interpretation. Here I consider this de Grothe and Lamarck system. Here, no, I omitted here this paper from 17. There's a bulletin of the sectional logic. Here is more model theoretic. Chwalowski, good journal. Girard, linear logic. De Grothe and Lamarck's classical non-associative Lambek calculus, the Studia Logica. Lambek, 2 classical papers. My PhD student Lin, and my last PhD student Wojciech. So, and one more, it is a Skatov and Van Alten by algebraic. They use algebraic method, but in fact, they proves that the universal theory of bounded residuated lattice ordered groupoid is X-time complete, but in fact, the proof yields that the quasi-equational theory this exactly correspond to the consequence relation of NL with additive connectives and the distributive law. So thank you. This is it. Thank you.
So, are there any questions?
Yes.
Including online, yes.
Online, so on the chat. Hmm? No, I don't see. Don't see chat.
No, there's no questions in the chat. What happened? Yes.
Because Eleni, she'll be on 18 here, one of the calls. She wanted to first present it, but then.
Okay, so.
Well, we lost the
slides. Could you, Wojciech, could you go back to share the slides again and go back 2 slides?
Okay. And where they are? Where they are. Here. Yes. No, and go. I should go back.
The first slide with the reference.
What?
Now she's
Should I go back?
Yes.
Uh-huh. But how to do it? Something is bad here.
So it would be nice if you are here
Oh,
on Friday. Yes.
back
The next one, the first with the references.
to. But what do
Go
what
page
slides are you interested in?
with the references.
Reference.
Yes.
26.
Okay.
Yeah. So this is the first paper they intended, Elaine, she mental, she intended to present it.
Who?
The first paper,
The first one?
yes, the very first one, Elaine, she intended to present it,
Pimentel, yes, Elaine
Yes.
Pimentel.
but then cost doesn't allow one of the authors to participate because he's from Russia.
But she
And she
doesn't
was very
participate.
disappointed and gave up. So, but she will be here on Friday on 18th.
She's from Brazil, yes, Brazil.
So try to be online. Maybe she'll ask you questions.
But maybe if you have some further interest, you can simply write to me. I don't know because I didn't publish here my email address, yes?
Yes, the very first
It is
paper.
very, very simple because I have, in fact, my university changed in last year, so I have two official mail addresses. But my many years I used very simple ones. The beginning of my name, Buszko, Buszko, yes, because I thought that my full name, first and family name are too difficult for foreigners, yes, and they will simply make mistake writing the mail address. So I use the logic Buszko, then this no, the sign, I don't say how in English it is called, and then one says Buszko Amu from Adam Mickiewicz University .edu.pl from Poland. So
So try to
this
be
works.
online on 14 or 18th because Eleni, she'll come on in person.
Yes.
And she'll have probably, she wanted to communicate with category of people.
Okay, so I will expect for some contact with her, yes?
Okay, so we seem to have exhausted the questions. So let's thank the speaker again.
Thank you.
Thank you for your attention. Thank you.
Philippe, would you?
Just to watch.
Okay, so we need to find Philippe.
You should stop recording. Yes, that's true.